All right, well, I guess it's time to get started. Welcome everyone to research session R24, I believe, on distributed and parallel data management. Please note that this session is recorded and will be made available afterwards. It will run for 90 minutes, contains 5 talks. Each talk gets about 18 minutes, 15 minutes for the presentation, and 3 minutes for Q&A. I know we're a small crowd, but still, please keep yourself on mute throughout the different presentations. There were some other instructions shared as well, such as click on your video settings and deselect the spotlight my video when speaking option. This goes for the non-speakers. Now, if you have any questions, you can either use the chat features, or since we're a small crowd, anyone who wants to ask a question at the end of a presentation during the Q&A, they can go ahead and unmute and ask the question. Finally, there was also a small scheduling change between the 3rd and 5th paper as for schedule on the original schedule. And the 5th paper, Fela, will be presented 3rd, and the 3rd paper, G-Thinker, will be presented 5th. With that, I think we're ready to get started with our first presentation titled SeeMoRe, a fault-tolerant protocol for hybrid cloud environments by Mohammad Javad Amiri from University of California, Santa Barbara. Mohammad, would you like to say something about yourself before we start the video?
Hey, hi everyone, this is Mohammad. I'm a PhD student at UC Santa Barbara, and I'm working on the area of consensus, blockchain, and fault tolerance.
Cool. Imrul, can you please start the first presentation?
Sure. Hello, everybody. I'm Mohammad Javad Amiri, a PhD student at UC Santa Barbara, and I'm going to talk about SeeMoRe, a fault-tolerant protocol for hybrid cloud environments. This work has been done in collaboration with Sujaya Maya, Professor Divi Agrawal, and Professor Amr Lebadi, all from UC Santa Barbara. Fault-tolerant systems tolerate machine and network fault by replicating data on multiple servers. To do so, we use a state machine replication, where all servers execute the same set of commands in the same orders. A state machine replication requires consensus among different servers on the order of these commands. Large enterprises usually have their own geo-replicated fault-tolerant clouds, such as Google Spanner or Amazon DynaMast. However, small enterprises usually have a small private cloud that is lacking resources to guarantee fault tolerance. For a small enterprise to provide fault-tolerant service, there are 2 options. A small enterprise can buy new servers and adds them to its private cloud, or it can rely on a public cloud. However, nodes in the public clouds are untrusted. It means they behave maliciously, whereas nodes in the private cloud are trusted. The question we want to answer in this talk is, can we benefit from both worlds, both private and public clouds at the same time? To answer this question, we need to define consensus. A consensus problem says we have a set of distributed nodes that they need to reach agreement on a single value. We can have different types of systems, like synchronous or asynchronous systems. In this talk, we focus on asynchronous systems. And we can have different types of failures, like crash or Byzantine failures. I'm going to introduce the crash fault-tolerant protocol Paxos, which is the most known crash fault-tolerant protocol. In Paxos, we assume that at most F nodes might crash concurrently. So once a node sends a message, it needs to ensure that the message has been replicated on at least F+1 nodes to make sure that one of them is correct. So we call this a quorum. So the quorum size is F+1. Any two quorums need to intersect on at least one node to guarantee total order. As a result, we have quorums of F+1s, and the network becomes 2F+1. In the algorithm, the pre-elected leader or the primary node sends proposal messages to backups. Once backups receive the message, the proposal message, they vote for that proposal. We call this phase decision making. And then the primary will make a decision on their vote. As can be seen, the Paxos has two phases. The message complexity is O of n, and the quorum size is F+1. The other protocol is PBFT, which is a Byzantine fault-tolerant protocol. In PBFT, the quorum size is 2F+1. We assume that we have at most F concurrent malicious failures. So we need the correct node to outnumber the malicious failures. So we need 2F+1 nodes. And the intersection of any two quorums needs to be F+1 to ensure that there is at least one correct node in the intersection. As a result, we have quorums of 2F+1, we have the intersection size as F+1, the network size becomes 3F+1. In PBFT, the first phase is the same as Paxos. We have the proposal, which is sent by the primary to all backups. However, we need a new phase, which we call it proposal validation. Why do we need this phase? Because the proposal is sent it might be sent by a malicious primary. So backups need to validate this proposal. To do so, they send message to each other. And if the proposal is validated, then they make a decision. The decision making is also all-to-all. Why? Because again, we cannot rely on the primary, which might be malicious, to make a decision. As a result, we have two phases of ON square. And in conclusion, we have three phases. The message complexity is ON square, and the quorum size is 2F+1. SeeMoRe wants to tolerate at most M malicious and at most C crash faults. Indeed, F is M plus C. The quorum size in SeeMoRe is 2M plus C plus 1. Why? Because we have M malicious failures. And we want the correct nodes to outnumber the malicious failures. So we need M plus 1 more nodes. It becomes 2M plus 1. However, C of them might crash. So we need C more nodes. As a result, the quorum becomes 2M plus C plus 1. The intersection of any two quorums is M plus 1. We use the same justification as PBFT because M of them might be malicious. As a result, the network size becomes 3M plus 2C plus 1. SeeMoRe has three modes. In the first mode, we assume that the primary is in the private cloud. Remember, the nodes in the private cloud are trusted or are crash only. And the backups are in both private and public cloud. So in the proposal phase, the primary sends proposal to all backups. And the backups send back their votes to the primary. Since the primary is trusted, the primary can make a decision by itself. We have two phases. The message complexity is ON. These two are like Paxos. However, the quorum size is larger. It's 2M plus C plus 1. We might want to reduce the load on the private cloud. The goal of the second mode is basically to reduce this load. In the second mode, the primary is still in the private cloud, so it is trusted. However, the private cloud is not involved in the second phase. Basically, the primary, which is trusted, sends a proposal to backups, and then we use 3M plus 1 nodes from the public cloud to make the decision. since they are untrusted, they might be untrusted. They kind of send a message together, and it's basically a decentralized decision making, which needs ON square type of messages. As a result, this mode needs two phases. The message complexity is ON square, and the column size is 2n plus 1. Note that in this phase, again, we don't need to validate the proposals because the primary is still in the private cloud and is trusted. In some scenarios, there might be a large network distance between private cloud and public cloud. And the clients might be closer to the public cloud. So in the third mode of SeeMoRe, we completely rely on the public cloud to process the messages. So the primary is in the public cloud. It might be malicious. And the private cloud is not involved in any phases. We again have the proposal, which is from the primary to all. We have the proposal validation because the primary is in the public cloud. And again, we have decision making. So it is very similar to PBFD. There are three phases. The message complexity is ON square, and the quorum size is 2n plus 1. We have done several experiments. I'm going to introduce a few of them. We implemented 4 different systems. One is the crash fault-tolerant protocol Paxos. One is the Byzantine fault-tolerant PBFD. We have another hybrid fault-tolerant protocol called Upright. Upright is very similar to SeeMoRe. It has the same model as SeeMoRe. However, it doesn't distinguish between crash failures and malicious failures. And we have these 3 different modes of SeeMoRe. And we basically measure performance, throughput, and latency. So in the first set of experiments, we increased the number of failures in different clouds, and we changed the basically number of C and M. So as you can see, these 3 different modes of SeeMoRe, which are basically the green is the first mode, the red is the second mode, and the purple is the third mode, are placed between Paxos and PBFD in most of the scenarios. And here is latency is the y-axis, and throughput is the x-axis. So the interesting thing is here is Upright, while it uses the same model as SeeMoRe, its performance is closer to the PBFD. It's worse than all modes of SeeMoRe in all scenarios because it doesn't distinguish between crash and malicious failures. Basically, where the crash failures occur and where malicious failures. An interesting scenario is where the number of crash failures is much more than malicious failures. As you can see, the second and third modes of SeeMoRe show better performance than even Paxos. The reason is in these 2, we rely on the public cloud to process requests. And since M is 1, these 2 needs 4 nodes, whereas Paxos here needs 9 and SeeMoRe needs 10. So the performance of these 2 modes is better than even Paxos. We also experiment the scalability across multiple data centers. We placed private and public clouds in 2 different data centers, California and Oregon. And at one scenario, we put clients close to the private cloud. So as you can see, different modes of SeeMoRe show kind of similar behavior to Paxos. Paxos is still better, but they are far from basically the performance of PBFD and Upright. In the next scenario, we put clients close to the public cloud, and some interesting behavior happens. As you can see, the third mode of SeeMoRe shows the best performance. The reason is in the third mode, we rely completely on the public cloud, and the clients are also close to the public cloud. So there is no need for cross-cloud communication. You see, there is 0 phases of cross-cloud communication. As a result, the third mode of SeeMoRe shows the best performance. And then we have the second mode, the first mode, the second mode, and other. So as conclusion, SeeMoRe is a hybrid state machine replication that tolerates both crash and malicious failures. in a public-private cloud environment. SeeMoRe distinguishes between crash failures that occur within the trusted private cloud and malicious failures that occur in the public cloud. SeeMoRe targets small enterprises that own a small set of servers and want to rent servers from public cloud provider. SeeMoRe has 3 different modes and can dynamically switch among these modes. SeeMoRe also has view change routines to handle primary failures. As a future work, SeeMoRe can be used in the context of permission blockchain system. With that, I end the presentation. Thanks for your attention, and I would be glad to take any questions.
All right, it is time to open the floor for any questions from the audience. Feel free to unmute and ask a question. Well, in all reality, it was very easy to follow talk. Very good job, Mohammed.
Thank you.
Personally, yeah, I don't have any questions. So thank you very much.
Thank you.
And we'll be moving on to the second talk for today on sharding open blockchains with smart contracts by Yuchen Tao from Hong Kong University of Science and Technology. Yuchen, would you like to introduce yourself?
Okay, I'm Yuchen Tao. I'm currently a PhD student in Hong Kong University of Science and Technology, and today I'm very glad to be here and introduce our work. Okay.
Mm-hmm. Thank you. Emil?
Sure, I'm sharing.
Mm-hmm. Perfect.
Hi everyone, I'm very glad to be here to share our work. First, I want to introduce blockchain systems briefly. So what is the blockchain? Traditionally, suppose 2 users want to conduct a transaction like money transfer.
Emil, I don't see a
centralized server like a bank will be.
Excuse me?
I don't see I just see a black screen.
Oh, really?
Yes.
Oh, excuse me for that. Let me play it from the beginning.
Hi everyone, I'm very glad to be here to share our work. First, I want to introduce blockchain systems briefly. So what is the blockchain? Traditionally, suppose 2 users want to conduct a transaction like money transfer. A centralized server like a bank will be responsible for checking whether that transaction is valid. However, in blockchain systems, there does not have such a centralized authority. So all the transaction histories are stored by all the miners. Therefore, all the transactions can be validated by all the miners. States and ledgers in blockchain systems are confirmed transactions stored by all the users, and miners are those validators who are responsible for validating transactions, and confirmed transactions will be packed into blocks by miners. So how does a blockchain system work? First, users will broadcast transactions through the point-to-point network, and if miners find that that transaction is valid, they will pack this transaction into a block and add this block to their own ledgers. Then this block will be broadcast to the network. However, the throughput in blockchain systems are not good compared to the traditional centralized systems. For example, in blockchain, in Bitcoin, which is a famous blockchain system, only 7 transactions can be confirmed per second. However, in Visa, thousands of transactions can be confirmed per second. Actually, the current blockchain system is a serialized system. We recorded the confirmation time of the same set of transactions with different miners in Ethereum, which is also a very famous blockchain system. In this table, we find that the confirmation time does not decrease. The reason for such a serialized nature is that each transaction must be validated by all the miners in this system. This is an example for such a serialized nature, and we first give some basic information. Miners can get transaction fees by validating transactions, and miners will validate transactions with the highest transaction fees at first. For example, so in this example, 3 transactions, A, B, and C, will be broadcast to the network. So only transaction A and C with higher transaction fees will be validated by all the 3 miners at first. In other words, only 1 block can be generated at a time. So sharding is proposed to improve the throughput. Miners and transactions are divided into multiple sub-communities randomly, and miners will only validate and store transactions belong to their communities. In this way, more than 1 block can be confirmed at a time. However, cross-shard transactions will appear if the separation is in a random manner. For example, A sends transaction 1 to boy in shard 1, and C sends transaction 2 to dog in shard 2. E sends transaction to F in shard 3. If A and C send transaction 4 to E, then information from shard 1 and shard 2 will be needed to validate transaction 4. And transaction 4 is called a cross-shard transaction. So why we do not prefer cross-shard transactions? First, the consensus protocol for validate such transactions are not easy to design. It is very hard to ensure that the validation results are synchronized among miners, even without malicious nodes. However, malicious nodes always exist. Therefore, the security will decrease. Second, frequent cross-shard communication will appear. For example, in OmniLedger, O(n)² communication times will appear during the confirmation process of 1 cross-shard transaction, and N is the number of users involved in this confirmation process. So we want to know if we can avoid cross-shard communication by intelligently distributing transactions into different shards. The smart contract gives us some hints. A smart contract records some transactions and some conditions. Under these conditions, those transactions will be self-executed. In this example, user A only incorporates contract 1 through transaction 1, and if transactions sent from user A form a shard, the validation of those transactions does not need any information from other shards. This is obvious. That is to say, no cross-shard communication is needed to confirm these transactions. Based on this observation, we introduce our design in detail. First, transactions whose senders only incorporate the same smart contract from a shard and miners only need to store transactions related to that smart contract. This is illustrated in the left figure. And however, there still exist some transactions whose senders participate in more than one smart contract. Therefore, those transactions will form a unique shard called the max shard. To validate these transactions, miners will store all the transaction histories in the system. These transactions are illustrated in the right figure. In these two cases, no cross-shard communication is needed for any transaction. However, just separating transactions according to smart contracts is not realistic. That is because miners can get certain coins once they successfully pack a block, whether they have added transactions into that block. Also, if the number of transactions in a shard is very high, the throughput improvement cannot be high. In the extreme case, all the transactions belong to the max shard, and in this case, no throughput improvement can be achieved. So we improve our design as follows. First, we need to let small shards merge into large shards. In other words, miners in small shards should mine transactions together. However, miners need to make some efforts during the merging process. For example, they need to communicate with others, and once the merging is successful, more miners will compete for validating transactions with them. In this way, we must provide some incentive for merging. Miners can get the shard reward in the form of coins once they have formed a large shard successfully. This is a cooperative game. The reasons are as follows. So first, miners will get different payoffs depending on others' choices, and also miners must cooperate with each other to get the corresponding payoffs. So considering that this is a cooperative game, we want to know how to achieve the Nash equilibrium with the proper algorithm. That is to say, how to ensure that miners do not change their decision at last. So we formulate the expected payoffs of miners and the replicator dynamics x dot, which is of the probability of using different strategies based on these payoffs. And we prove that if and only if the replicator dynamics is zero, the system is in the Nash equilibrium state. Therefore, we use this formula to ensure that we can achieve a zero replicator dynamics which means the xi, the probability of using different strategies does not change. And for shard with too many transactions, we want to let miner select different sets of transactions. This is actually a congestion gain. Recall that only one miner can get the transaction fee of a transaction as we have discussed before. Therefore, miners must compete with each other to maximize the transaction fees they can obtain. Further, other choices will always affect a single miner's profit. So, the same question becomes how to achieve the Nash equilibrium. According to the existing works, the base reply strategy can be applied. With the base reply strategy, miners will select transactions with which their expected payoffs can be improved. And another question related to our intra-shard algorithm is that the communication cost may be high because miners need to exchange their choices during this two-gaming process. And the observation is that our two merging and transaction selection algorithms are deterministic. Therefore, if we just let all the users have the same initial parameters, they can just calculate the results locally. In this way, the communication overhead is O1. Then we evaluate our design. First, we will record different waiting time for confirming the same set of transactions using different schemes and methods. We first compare with chain space. We find that our design will perform better when the number of shards is larger than 4. And during the evaluation of our two inter and intra-shard algorithms, in the left, we can get two basic conclusions. In the left figure, we can find that there will be 90% more empty blocks without our inter-shard merging algorithm. And in the right figure, we can find that our intra-shard transaction selection algorithm can improve the throughput by 3 times on average. And that's all.
Well, that's great. So, any questions from the audience?
I could ask a question. So I'm
Please.
curious about what kind of benchmarks you are using, because from what I understood, you're going to merge different shards if they share, if there are connections that, if there are inter-shard transactions, and then you might end up with everything in one big shard. So I'm curious, what is the data distribution that you are using, and what kind of, yeah.
Okay, so you have two questions, right? The first question is about the benchmark. Actually, we have two benchmarks. The first one is the chain space, which is an existing work about sharding transactions into different shards evenly. So the difference between chain space and our design is that we will separate transactions into into shards with different numbers and different distributions, and then we will merge these small shards into large ones, and large ones will be in large ones we will let minor select different sets of transactions. So the first benchmark is that we will compare the throughput improvement between the chain space and our work to evaluate our basic design on sharding transactions into different shards, not evenly. So the second benchmark is just the Ethereum. Since the existing sharding all the existing sharding mechanisms just separate transactions into shards even. So to evaluate our inter and intra-shard algorithms, we can only compare the reduction of the empty block and this throughput before and after our algorithms, because that does not exist in such mechanisms. Other sharding mechanisms just distribute transactions into shards evenly, so they do not need to merge or select etc. So this is the first question, and the second question. Our design is implemented based on the Ethereum, and it is our platform is the Amazon EC2. So, and the second question is about the data distribution during the evaluation on the inter and intra-shard algorithms. Actually, we just in the inter-shard, during the evaluation about the inter-shard merging algorithm, we just let my transaction. Let me think about it. Actually, we just randomly inject transactions into different smart contracts, and there the data distribution between different small shards obeys the normal distribution. No. Let me think about it. What? I cannot hear.
You're muted.
Yeah, I think, thank you very much. I think that's enough. It's taking too long.
Okay.
We can, if we have more questions, I'll send you an email. Thank you.
Okay, thanks.
It turned out it was a loaded question. All right, I think we need to move on to the next presentation. Thank you, UHN.
Okay, thank you.
So our next presentation is Fela, incorporating flexible parallelism and elastic tuning to accelerate large-scale DML by Jinkun Zheng from Tsinghua University. Well, I guess now he's at Stanford. Jinkun, would you like to briefly introduce yourself?
Yes. Hello, everyone. I'm Jinkun Geng. I'm currently a first-year PhD student in Stanford University, and my research interest mainly focuses on networking and system. And today, I'm very glad to be here to show you with our works. Thanks.
Hello, everyone. I'm Jinkun. Today, the topic I would like to share with you is Fela, incorporating flexible parallelism and elastic tuning to accelerate large-scale distributed machine learning. And this work was cooperated with my supervisor, Professor Dan Li, and also my partner, Mr. Shuai Wang. As we all know, distributed machine learning has become the common practice, and this is mainly due to two reasons. First, the training data has grown to a huge volume, and also the training model is becoming more and more complex. So in that way, we cannot use one single machine to handle such tasks anymore. And we need to use multiple machines to train the task in a distributed way. So to coordinate DML workflow, we can use data parallelism, model parallelism, and also hybrid parallelism, which are very familiar to DML process. But reviewing the existing solutions to DML, there are two outstanding issues. One is flexible parallelism, and the other is straggler mitigation. So what is the flexible parallelism? While we are training a big model, for different parts of the model, they may need different parallelism degree in order to achieve the highest performance, which means in order to fully utilize the GPU power. Let's take the commonly used VGG19 model as an example. When we are training the front-end layer of the VGG19, for example, if we are training the layer 64, 64, 224, and 224, if we are training this layer, it requires about 16 batch size in order to reach the maximum throughput, which means it can fully utilize the GPU with the batch size of 16. But while we are training the backend convolution layer, say this layer, we may need about 64 batch size in order to saturate the GPU. So in other words, the backend convolution layer needs higher parallelism degree to fully utilize the GPU power. And another issue is the straggler problem. When we have multiple workers, but different workers have different speeds, the overall performance of the DML task can be slowed down by the slowest worker, that is the straggler. So one straggler can slow down the overall performance, and it will cause waste of the computing. It will waste the computing resource for the other fast workers. And to be more specific, we have compared the existing solutions to DML in 5 dimensions. So you can refer more details in our paper. But unfortunately, none of the existing solutions can cover the 5 dimensions. So in order to achieve a better performance than the existing baselines, we decided to design our own solution. In our design of Fela, we also use a hybrid parallel way to execute DML. But the most innovative point is that we leverage the abstraction of token to represent each submodel. So in that way, we can shape the DML task into a token scheduling problem. Here is now workflow. Given a very big model, we can first do some offline profiling. For example, we can profile each layer, and then we can obtain the optimal parallelism degree for different parts of the model. Then, with some heuristic partition method, we can partition the big model into several submodels, and within each submodel, they can use the same parallelism degree to achieve a better utilization of the GPU power. And after that, we can represent each submodel with one type of token. Here we can see that we have partitioned the big model into 3 submodels. So in that way, we generated 3 types of tokens and use these 3 types of tokens to represent different models. And then the DML task becomes the problem of token scheduling in order to achieve the best performance. And here is now architecture design. As we can see, I will not touch too many details here, but in a simple way, we can see that we build a token server, which is responsible for distributing the tokens to different workers. And each worker will communicate with token server. They will come to ask for tokens, and with some elaborate token scheduling policies, we will distribute the proper token to each server. And after the server has obtained the token, it will train the submodel corresponding to that token by fetching some the required parameters from its local memory or from the remote workers. And after it has completed the training, it will report the completion to the token server and access new tokens to continue their training. So in that way, token server plays a reactive role So long as you work faster, you can come to fetch more and more tokens, and you don't. In that way, you can compute more workload, and so different workers can coordinate in a friendly way. And here I want to illustrate now token-based scheduling. As we have mentioned, here we have 3 types of tokens, but different tokens corresponding to different submodels, and these submodels have different parallelism degree. Let's suppose submodel 1 needs a batch size of 16, and submodel 2 needs a batch size of 32. So in that way, we need to have more T1 tokens than T2 tokens. Specifically, we need to have twice as many as T2 tokens for T1 tokens. And at first, there are only T1 tokens available in the token bucket. After some workers have completed the T1 tokens, based on the T1 tokens, we can generate T2 tokens. And with 2 completed T1 tokens, we can generate 1 T2 token. And how to schedule these tokens to these workers? We have designed 3 types of scheduling policies. And the first one is aggressive death-first scheduling policy, which means when there are multiple tokens coexisting in the token bucket, we will first distribute those tokens which has a high level. For example, here we have both T1 tokens and T2 tokens. So we prefer to schedule T2 tokens at first. But when there are multiple T2 tokens, we will secondly consider the locality, which means, for example, if the worker comes to request for new tokens, and the worker has just completed training token 2 and token 3. So in that way, the required parameters for token 9 will probably be located on that worker. So in that way, we prefer to distribute token 9 to that worker first instead of token 10. And in our paper, we have used a metric called locality score. And when there are multiple tokens inside in the token bucket, we will first distribute the tokens with the highest token score. And the second policy is the hierarchical fetching policy. That means instead of maintaining a very large token bucket and each worker comes to contend for the tokens, we have divided the token bucket into several sub-token buckets. So each worker will first come to consume the token in its own STB. Only after it has consumed all the tokens in its sub-token bucket will it come to consume the token in other sub-token buckets, which means only after the worker has finished its own workload can it come to share the workload of the other straggler workers. And for the third policy, we have designed a conditional token distribution policy because we noticed for some submodels, they can be very communication intensive, but the computation workload is not very high. So to reduce the communication workload for these submodels, we will constrain the distribution scope for them. That means for a certain type of tokens, we will distribute them only to a subset of workers. So only the workers in that subset will compute these models and synchronize the parameters in a small scope. So in that way, we can reduce the communication overheads for that model and accelerate the overall performance. And as for the experiment, we have used an 8-node cluster, and we have designed 3 baselines, 2 benchmarks. We have also compared their performance in both non-straggler scenario and the straggler scenario. So as for the non-straggler scenario, we can see the average throughput. That means how many images can be processed in 1 second. For the average throughput, Fela has improved by 9.9% to 12 times. And in the straggler scenario, we have designed two straggler scenarios. For the first one, that is the round-robin straggler scenario, the AT has been improved by 9.7% to 4 times. And for the probability-based straggler scenario, the average throughput has been improved by 19% to 4 times. So in conclusion, Fela has shaped DMR into a token-based scaling problem, and it can incorporate flexible parallelism and elastic tuning so as to achieve a much better performance than all the baselines. And as for the future extension of Fela, there are two main directions. First, we want to make Fela a more general framework. Currently, Fela only supports CNN training tasks, but in the future, we can make Fela support other DML tasks such as PageRank, such as matrix fractionalization, and so on. And the second direction is that we want to improve the compatibility of Fela. By adding an attribute of age to the token, we can make Fela compatible to ASP and SSB training. And that is all about our work. And I'm ready to have your questions.
All right, that's great. So do we have any questions for Jinkun? So while people are thinking, I actually have a question. You mentioned at the beginning that you first do an offline phase, to get the profiles. How expensive is that phase, especially compared to the benefits you're getting afterwards? And are there any trade-offs that we need to be aware of?
Yes, actually, that is a good question. It can be considered as a trade-off between the granularity of the control and the performance. That means if you partition the model into the final granularity, for example, if you partition the model into layer by layer, then you need to off-file each layer to get the performance, to get the parallelism degree. But if there are many layers, you can just use the coarse-grained granularity. That means you can cut the model with you can cut each part into several layers, and you only optimize in a coarse-grained granularity. But one thing to note is that even if we maintain a fine granularity, that means even we spend much time in the offline profiling, it is a once-for-all procedure. That means, for example, for different convolution layers, for different convolution networks, there are only a certain number of convolution layers. So you can offline, you can profile each layer once, and then you can apply it to different models. So in that way, the marginal cost is not very high.
Good, thank you. Any other questions for Jinkun? Seems like we have a shy crowd today. All right, well, thank you, Jinkun. Let's move forward to our fourth presentation for today, DynaMast, Adaptive Dynamic Mastering for Replicated Systems by Michael Abebe, a PhD student at University of Waterloo. Michael, would you like to introduce yourself?
Hi, everyone. I'm Michael, and I hope you enjoy our work on DynaMast. And feel free to ask any questions at the end. Thanks.
Hi, everyone. I'm Michael, a fourth-year PhD student at the University of Waterloo. Today, I'm excited to talk about DynaMast, our distributed database system that adaptively changes data mastership in response to the workload. This work, which you can find online, was done in collaboration with my colleague Brad Glasbergen and our advisor Kazana Dowji. Let's start by discussing database scalability bottlenecks and how dynamic mastering addresses those concerns. Consider a single site database that stores 4 data items, A, B, C, and D. A client interacts with that database and submits transactions. As there is only one database site, all transactions can be committed at that site. Hence, all transactions are single-site transactions. However, as this database stores all data at a single site, as load increases on the site, eventually the database system will become overloaded, resulting in degraded system performance. To avoid this bottleneck, the database must scale to multiple sites. There are two common approaches to scaling a database: a single master architecture or a multi-master architecture. Each of these approaches have pitfalls, which we will demonstrate, starting with the single master architecture. Then, we will show how our approach, dynamic mastering, overcomes these challenges. In the single master architecture, all updatable or master copies of data are located on a single master site. Other sites store read-only replicas, indicated here by lowercase data items. In the single master architecture, update transactions, or writers, execute and commit their transactions at the single master site. These updates are then propagated to the replica site, where read-only transactions execute on the replicated data items. Thus, in this architecture, just like the single-site database, there are no distributed transactions, because all transactions execute and commit at a single site. Unfortunately, as with the single-site database, the single master has a scalability bottleneck. All update transactions execute at the single master site. Thus, as the number of update transactions executing increases, the single master site becomes overloaded. Therefore, although the single master distributes transactions among sites, it still suffers from a single site bottleneck. Let's now examine the alternative approach to scaling the database, multi-master. In the multi-master architecture, the master copies of data are distributed among the sites. In this example, the master copies of data items A and B are located on data site 1, while data items C and D are mastered on the second data site. Clients updating data item A or B execute on one data site, while clients updating data item C or D execute on the other data site. Hence, by distributing the master copies of data, the multi-master architecture distributes the load among the sites and avoids a single site bottleneck. Let's examine how multi-master executes a transaction that updates data items A and C, which are mastered at multiple sites. First, the updates execute at each site independently. To ensure atomicity, the system uses the ubiquitous two-phase commit protocol, or 2PC. In the first phase of 2PC, the protocol consults with each site to see if they are prepared to commit. If all sites are willing to commit, in the second phase of 2PC, the protocol sends commit messages to each site. This protocol is a blocking protocol, as between the phases, each site is uncertain of the global outcome of the transaction. Thus, subsequent transactions accessing the same data items, such as this update to C, are blocked during this period of uncertainty. Consequently, multi-master suffers from needing a costly coordination protocol, which many studies have shown results in significant performance drawbacks. This slide summarizes the strengths and weaknesses of the multi-master architecture and the single-master architecture. Ideally, we want to build a system that provides the strengths of both of these architectures, that is, distributing load and single-site transaction execution. In this paper, we describe how we achieve these properties with dynamic mastering. Dynamic mastering uses a replicated multi-master architecture, as shown on this slide. Let's consider how the transaction which caused costly overheads in multi-master works in DynaMast. In contrast to the traditional multi-master architecture, dynamic mastering executes this transaction by remastering data item A from data site 1 to data site 2. Doing so results in data site 1 containing a read-only replica of A, while the second data site now contains the updatable master copy of A. Observe that now A and C are mastered at the same site, so the transaction executes at the site without coordination during the transaction. That is, the transaction executes as a single-site transaction. Note that if the same data items, A and C, are updated again, perhaps due to locality in the workload, dynamic mastering provides long-term benefits, as we remaster only when necessary. Here, the transaction can execute at a single site without further dynamic mastering, thereby amortizing the overhead of remastering. By contrast, costly coordination with TPC repeatedly occurs in the traditional multi-master architecture. However, unlike the single master architecture, as dynamic mastering distributes the master copies of data items among sites, update transactions are distributed among sites, which distributes the load. A key characteristic of dynamic mastering is that it occurs before transactions execute. Hence, remastering occurs outside transaction boundaries, unlike in 2PC. Thus, other transactions can execute while remastering occurs, as no site is blocked by the uncertainty of a transaction's outcome, which allows greater concurrency, in contrast to 2PC. We implemented dynamic mastering and its architecture in a system called DynaMast, which is a distributed and replicated database system that performs dynamic mastering adaptively, that is, based on the workload, and thus provides both single-site transactions and load balance among sites. Given this overview of dynamic mastering, two key challenges arise. The first is how to perform remastering efficiently. The second is how to decide where to master each data item. Let's start with how we address the first challenge and revisit our example that remasters A from the first to the second site. The key insight is that we can make remastering efficient by exploiting replicas. That is, by having a replica of a data item, we can change its mastership with a simple metadata operation that changes the mastership status at a site. I'll demonstrate how remastering occurs in a bit more detail by going back to our initial master placement. In this master placement, a client executes an update to data item A, as indicated by this golden color A, which updates the master copy of A to gold at the first site. This transaction commits, so we remove the client from view. Using our running example that wishes to update data items A and C, we wish to remaster A from the first site to the second site. If we simply use the fact that the second site has a replica of A and change the master, we see that at the new master of A, the second site, A is still blue. The second site is missing this golden update from the first site. This naive change in mastership produces inconsistent state, as we have effectively lost the update. To address this concern, we introduced two key rules to ensure consistency. First, the old master must not allow new updates to the data item after it was remastered. And second, the new master must have applied all previous updates to the data item being remastered. To achieve these goals, we introduced two messages, release and grant mastership, which we now illustrate by example. The system first sends the release mastership message to the current master. This results in the first site becoming a replica of A. Hence, no new updates occur to this data item at this site, and the release operation completes. Then, the system sends data site 2 the grant message, which blocks until A is up to date. As data site 2 is a replica of A, all updates to A from data site 1 have been propagating to this replica of A, such as this golden update to A. With this golden update, the two data sites reach the same state for A, and the grant operation succeeds. This results in data site 2 becoming the master of A, and the grant operation can now complete. Now the transaction can execute at data site 2. Importantly, while the release and grant of A occur, transactions can concurrently execute on other data items. Now I was showing you this worst case behavior to ensure that the new master has all previous updates. In reality, the new master was a lazy replica of the old master and continuously applying updates. Hence, there is little time spent waiting for updates, as the new master typically needs to apply only a few updates before remastering completes. For further details on the remastering protocol and a proof of correctness, please see our paper. Let's now examine how we address the second key and important challenge, how to decide where to master data. I'll describe this challenge using our running example that remasters A from the first to the second site. Then, given a subsequent transaction that updates A and B, we have to remaster either A or B. If we naively remaster B to the second site, then we end up in the single master architecture with all of its pitfalls. However, if we remastered A back to the first site, to evenly balance the number of masters among sites, what happens when we receive another transaction that accesses A? Without care, we could end up remastering A back to the second site. Doing so results in ping-ponging the mastership of data among sites. Hence, we need intelligent strategies to decide where to master data. To do so, we introduce a site selector that adaptively decides on remastering based on the workload. Our remastering strategies work as follows. The site selector tracks data access patterns based on the transactions submitted to the system, as well as site loads. And given these tracked statistics, the site selector quantifies the benefit of remastering to each site. This benefit is based on the effect remastering will have on load, how remastering now will affect future remastering, and the expected latency of remastering based on update propagation delays. Given these benefits, the site selector remasters to the site that maximizes the expected benefit. Our paper contains full details on our remastering strategies. So the question now is, how well does our approach work? We evaluated DynaMast using several popular workloads, including YCSB that contains multi-data item transactions using scans and read-modify writes, as well as both uniform and skew access patterns. We also evaluated with TPC-C that models an order entry application and contains complex updates and reads. We compared DynaMast to 4 other systems, including the fully replicated single and multi-master architectures. We also compared against single copy systems, including the partition store architecture based on HStore, which is similar to multi-master but lacks replicas, and Leap, which modifies partition store by localizing transactions by copying the required data to a site for transaction execution. We first perform experiments with YCSB using a write-heavy workload with Skew and show throughput. DynaMast outperforms its competitors with more than 1.6 times greater throughput than Leap and single master, and up to 10 times greater throughput than multi-master. To understand this significant improvement in throughput, we examined where transactions were routed in the system. We see that DynaMast evenly routes the transactions among the 4 sites, resulting in even distribution of load. By contrast, single master routes all write transactions in the write-heavy mix to the single master site. Consequently, the single master site receives 3.6 times more load than a site in DynaMast, resulting in overload. Due to the skew in the workload, partition store and multi-master also fail to balance the load among the sites. Finally, Leap exhibits similar trends to partition store and multi-master, but has greater variation due to its dynamism, but lack of intelligent strategies. Next, we examine the latency of the new order transaction in TPC-C, the most frequent and representative transaction in the workload. On this log scale graph, we see that DynaMast reduces latency compared to its competitors significantly. DynaMast reduces latency compared to single master by 40%, by distributing load across all sites. And compared to Leap, DynaMast reduces latency by up to 96%. Our paper contains many more detailed experiments that show the benefit of DynaMast. So to summarize our work on DynaMast, we outline dynamic mastering, which guarantees single-site transactions, thereby reducing overheads compared to costly distributed coordination protocols present in traditional multi-master architectures. We remaster efficiently by leveraging replicas and having our protocol occur outside transaction boundaries, which eliminates uncertainty about commits. Finally, using comprehensive and adaptive strategies, we balance load among sites and minimize future remastering. And you can find out a lot more information about our work in our paper. Thank you for your time.
Hi, great, thank you. All right, so any questions for Michael?
I have a question. Very nice presentation, thank you. I had a couple of questions. So a technical one is, since you have an adaptive remastering approach, what if you're in the long tail and you know that this particular object is not going to be accessed very often? Do you sometimes avoid the remastering completely since it's not worth it?
So in our paper, we always do remastering, and one of the things that we take into account when we make a remastering decision is the relative frequency of access, and in particular co-access. So if in your situation where you're saying like, this data item isn't accessed very frequently, that means there's not a lot of updates to that data item, so there's very little update propagation delay.
Or really updates with another object that is far away. That is more the issue. I mean, that's why you do the remastering.
Right. So
I mean, it might be frequently accessed, but not by itself, for example. And every now and then you go and update something else with it.
I see. Yeah. Okay. So I misunderstood your question a bit. So yeah, so you have a frequently accessed data item that is infrequently accessed with other data items. So again, because we take into account the co-access when we're making these decisions, that would kind of go into our adaptive strategy, and we make that decision that says, this is very heavy on this site. There's a big cost of moving that, remastering that data item away. So remaster the data item accessed with it to that same site. Now, this has an obvious conflict, which is, well, what if the other thing that you're accessing is also very popular, right? And so in our paper, we did an experiment with this with TPC-C, where we increased the frequency of these so-called distributed transactions. And what we observe is that our strategy converges to the single master, because in that case, that is kind of the best that you can do if you have these frequently accessed data items co-accessed together. So I hope that answers your question.
Yes, I had another more philosophical question.
Okay.
When you started the presentation, it kind of was leading towards a sharding-based approach. Why did you decide, to incorporate replication as well? Is it necessary for the approach, or is there benefits of fault tolerance which are typically associated with replication?
Yeah, so that's a good question. So there were two kind of thoughts on this. The first was that in our experience, people frequently have replicas of data. The single master approach is one of the most popular architectures. So we thought, how can we leverage that? And that's why we went down the replication approach. And once we had it in our mind that we wanted to do things adaptively, how can we leverage replicas to make that remastering efficient? So that was the philosophical approach that we took. Yeah.
Thank you.
No problem.
All right, well, I have a more technical question, I guess. I'm curious to what kind of a replication mechanism did you use?
Yeah, so we were using lazy replication that was logical. So it wasn't like physical, like log shipping. It was, what are the updates of these transactions? And we propagated these with Kafka. So in the paper, we have a lot of details about this, but basically we write the redo information into a Kafka stream, and then replicas subscribe to this stream and apply the logical updates to the data items.
So statement-based replication, is that what you mean when you say?
No, so it wasn't statement, because if your transaction was a read of a data item and then do something else based on that read, the replica might be at some further state ahead of where that read occurred. So it was logical in terms of this was the update this data item to this value.
I see. Cool. All right. Thank you.
Yeah, no problem.
Yeah, it was a very interesting talk.
Thanks.
All right. Any last questions before we move on? All right. Seems not. All right. Thank you, Michael. So moving on to the last talk for today, gthinker, a distributed framework for mining subgraphs in a big graph by Dr. Da Yan from the University of Alabama. Yes.
Thank you everyone for staying till the last talk of the session. I'm Daniel Yan, and feel free to ask questions at the end. Thank you.
Hello everyone, my name is Da Yan, and I'm an assistant professor from the Computer Science Department of the University of Alabama at Birmingham. I'm here to present our ICD 2020 paper titled G-Syncer, a distributed framework for mining subgraphs in a big graph. First, let me introduce our target problem. That is, to find qualified subgraph instances from a big graph. One example is to mine dense subgraph structures, such as cliques, quasi-cliques that requires each node to be connected to the majority of other nodes, and many other dense subgraph definitions. Another example is subgraph matching. We are given a query graph. We want to find the subgraph instances that match it in a big data graph. This query is useful in searching knowledge graphs and biological networks. A key feature of those problems that we target is that the time complexity is high, often because of the giant search space, rather than the data volume itself, as in conventional data-intensive analytics. In this slide, we show how we can explore the vertex set of a result subgraph by depth-first backtracking in a set enumeration tree over all possible vertices. This, for example, applies to our clique finding problem. To avoid redundancy, we only add new vertices into the set if their IDs are larger than those vertices that are already in the set. For example, to get ABD, we do not grow BD by A, but rather grow AB by D. In traditional single-threaded algorithms, we usually solve these problems by divide and conquer that backtracks on the nodes in our previous set enumeration search tree. Let us illustrate by considering the problem of finding maximal cliques. Specifically, since each clique is a complete graph where each pair of nodes are one hop away, we can construct one-hop eagle networks around each vertex and find cliques from those subgraphs. If a vertex, say V1, has a high degree and so the subgraph around it is still very big, we can recursively divide it into small overlapping subgraphs for further mining. Now, let's zoom in that subgraph and assume that V1 is already in our result clique. We can then consider two cases: those cliques containing V3 and those without V3. The pink subgraph assumes V1 and V3 are in our clique already, and we continue mining cliques in this subgraph by kicking out those vertices more than one hop away from V3. For those without V3, we can further divide them into those with V4 and those without V4. The pink subgraph assumes V1 and V4 are already in our clique, and we kick out those vertices more than one hop away from V4 from the subgraph and then continue the mining. We can then continue on the remaining subgraph and divide it further if necessary. In fact, the mining itself follows this recursive procedure and explores our set enumeration tree in depth-first order. We next review the related works that tackle this problem. Earlier works use MapReduce for dense subgraph mining problems like triangle counting, but as the TKDD paper in this slide shows, the authors found that MapReduce is not suitable for triangle counting. The fastest MapReduce algorithm at that time takes over 1,600 machines for more than 5 minutes to find the triangles of a graph on which the author's single-threaded algorithm only needs half a minute. This is a huge waste of computing resources and energy. Due to the popularity of things like the Vertex programming model, there are some works solving dense subgraph mining and graph matching using Vertex-centric programs. However, in the Vertex-centric paradigm, vertices notify other vertices about their value update by sending messages along edges, making the execution network I/O bound. Also, the programming is not intuitive for subgraph mining, since Vertex-centric programs operate in the unit of vertex and are usually for computing values for vertices, not for finding subgraphs. Recently, a number of systems were proposed for graph mining based on the idea of subgraph-centric programming, which is more intuitive. However, they only address the programming friendliness issue, but not the low efficiency issue, as their execution engines are still IO-bound. Nscale is the first work in this direction, which constructs candidate subgraphs to mine upon around each vertex, using k iterations of breadth-first search. However, this is conducted by k MapReduce jobs, which makes the process network IO-bound. Each MapReduce job also needs to load and dump a huge amount of intermediate subgraphs via Hadoop digital file system. The subgraphs are then finally distributed for concurrent mining with another MapReduce job, which separates from the curse of the last reducer. Arabisk proposes a user-friendly programming interface for graph mining called embedding-centric program. Here, embedding is the materialized subgraph, and these subgraphs are grown in increasing size for checking. Arabisk is a distributed system where every machine needs to keep an entire data graph in memory, and the subgraph materialization makes it network I/O bound. In contrast, our G-Syncer uses node backtracking in serial mining algorithms as much as possible to avoid the cost of materializing subgraphs. Arabisk's API also covers the problem of frequent subgraph pattern mining which requires Arabic to conduct subgraph isomorphism check on every newly materialized subgraph. But such check is not needed in other subgraph mining problems that we consider. Recall that our stat enumeration tree perfectly divides the search space and avoids redundancy by comparing vertex IDs. In summary, Arabic's API is simple, but not amenable to efficient execution. Check out our prefix FPM system for a more efficient solution for frequent pattern mining. In fact, removing the slow network communication can speed up the computing, as is done by the upstream system. But as a single machine system running out of core, upstream is still disk I/O bound. Another system, Nuri, proposed to find the top K result subgraphs rather than all of them. But Nuri is a single-threaded Java program. All the systems we reviewed so far do not scale their performance with the number of CPU cores they use. For example, on a dataset called YouTube, Nuri takes over 1,000 seconds to find clicks. If you use our G-Sync system on the same graph, which has 1 million vertices, it takes only 9.4 seconds on a vertical machine. You're welcome to check out our demo on the G-Sync website. As a side note, Frank McSherry has criticized the I/O-bound bottleneck of existing big data systems, whose performance is often only comparable to a single CPU core throughput. I started a new paradigm called T-Syncer, or think like a task, which targets high complexity divide and conquer algorithms over big data. The idea is that if your computing cost is superlinear to data size, the cost of computing a task on a subset with data is expensive enough to justify the I/O cost of collecting the data subset. Of course, we should still keep the programming model more general and friendly than using a conventional HPC library. There are many problems amenable to divide and conquer. And here, there are a great amount of real research opportunities for systems researchers. I was a veteran of systems in the Vertex-centric paradigm, and my experience tells me that T-Syncer paradigm is the next gold mine. We will also have a new book chapter coming, sharing our experience developing such systems. And you're welcome to check it out. Here is a brief history of our G-Syncer system. G-Syncer was originally a prototype when I proposed a Vertex pooling-based subgraph API, but as a prototype, the execution engine is just to make things work, and it does not even have multi-threading support. It also has flawed designs, say, tasks access vertices in bulk synchronous manner, and to reduce memory overhead, subgraphs are saved to disks, but a bad task scheduling strategy leaves many subgraphs on disk, leading to expensive I/O costs. Since a full-fledged G-Syncer system will take time to develop, the student who helped implement the old G-Syncer added multi-threading support and termed the resulting system G-Miner. But it inherits all the flawed designs and leads to poor performance when the input graph gets big. G-Miner follows the same API as G-Syncer. Please check out our new G-Syncer website where you can find great documentation, and my group will provide full technical support. Here's an overview of G-Syncer in a cluster of 3 machines. G-Syncer loads the input graph from HDFS, where each machine loads a fraction of vertices along with their adjacency lists into a local table. Tasks are initialized from each vertex in the local table, and the task can grow its subgraph by requesting neighboring vertices, or actually their adjacency lists. To allow multiple tasks in a machine to share remote vertices, a remote vertex cache is maintained, but it has a capacity limit to keep memory bounded. Each computing thread maintains a local task queue to keep it busy. This is the key to our scalability to CPU cores. When the task queue is about to be empty, new tasks will be refilled to the queue, while if more tasks need to be added to a full task queue, the last batch of tasks in the queue will be spilled to disk to be refilled by other computing threads later. This allows the memory consumed by tasks to be bounded. Here's an illustration of how vertices are partitioned by the local vertex tables of all machines, which form a distributed key value store where a task can pull the adjacent list of a vertex using its ID. Here's an illustration of the remote vertex cache. For example, while vertex 8 is not in machine M0, if a task on M0 requests vertex 8, it will be pulled to the cache. Note that if another task on M0 also needs 8, it can then directly access it in the cache without sending a duplicate request. Here is the task-centric programming model of G-Syncer. The first user-defined function specifies how a task is spawned from an individual vertex. The second user-defined function specifies how a task grows its subgraph from those surrounding vertices adjacency lists, which are pulled into the frontier array the last time the compute function is called. A task calls compute function in iterations to expand its subgraph until all needed data are ready, after which the task then mines the constructed subgraph. When vertices are being pulled, the task is suspended so that CPU cores can be released to process other tasks. A task can pull a vertex that is on its subgraph boundary. It can also split the subgraph into multiple new tasks for concurrent processing if the subgraph is big. The next question is how to design our remote vertex cache so that tasks can access vertices concurrently, while requested vertices can be continuously added from remote, and the vertices no longer needed by tasks can be evicted to make room for new requests. One solution is to hash vertices into different buckets using their IDs, so that if two vertices are in different buckets, their processing can happen together. In this slide, we assume vertices are hashed to 10 buckets by hashing their IDs modulo 10. Each bucket is protected by a lock so that only one operation can be carried out each time. A bucket has 3 containers. Gamma table keeps the adjacency lists. Z table or zero table tracks which vertices are no longer needed by tasks. And R table or request table keeps those vertices that are requested by tasks, but whose adjacency lists are still on their way. We next illustrate how these containers are used. For example, if some tasks requests remote vertices 10 and 11, and their adjacent lists happen to be already in gamma tables, then we simply add their counters by 1 to indicate that one more task is holding them. Here, vertex 10 is also removed from the table as its counter is no longer 0, and it cannot be evicted anymore. Next, we assume a task finishes a round of compute function and releases its hold of request vertices, such as 12 and 13 here. Then we need to decrement their counters in the gamma table. And since vertex 12's counter becomes 0, it is added to the table to allow eviction. Now assume a task requests vertices 20 and 21 from our cache, and their adjacency lists are not already in gamma tables. Then we need to add them to R table. Here, 20 is already in R table, and so we simply increment its counter to avoid sending another redundant request, while 21 is a newcomer, and thus the request is added to the sending queue. Note that R table avoids sending redundant vertex requests. Now assume that vertex 22's adjacency list is right, and in R table, 22 already has 3 task requests. Then we move this entry along with its counter 3 to gamma table, indicating that 3 tasks are holding vertex 22. We also have a garbage collector that periodically scans Z tables to evict vertices. That's why we need the small size Z tables. If we let GC scan the larger gamma tables, it will take a longer time to tag each bucket, and hence reducing concurrency. An evicted vertex is removed from both Z table and the gamma table. Next, we look at G-Synchronous task management. In this slide, the components in the red box are shared by all computing threads in a machine, including the local vertex table and a list of task files spilled from the task queues of computing threads, both of which are sources of tasks to be refilled into task queues. The black box on the right shows the components for each computing thread, where the third task source is a set of tasks that are waiting for the request data to arrive. We will prioritize our refill by considering the task files first, as these tasks have been partially processed, and we want to finish pending tasks earlier than spawning new tasks to process, in order to minimize the number of disk buffered tasks. Now, let's look at those components inside each computing thread. The task queue keeps a list of tasks to be computed by the current thread, along with their vertices to request for. If the queue has too few tasks, we will refill tasks from one of the previous 3 task sources. If the queue is full but a new task needs to be added, we will spill the last batch of tasks as a file to disk. Each computing thread pops a task from the head of the queue each time, requests the vertices, and if any of them is not in the cache, it will put the task into the task table shown here to wait for data. We also keep track of how many requested vertices are met. If a vertex response is received, we get the task list of that vertex from the R table. We mentioned we maintain a counter for each R table vertex entry, but we actually maintain the list of task IDs instead to track those tasks that request that vertex. For each task in the task table, we add the map counter, and if the counter reaches all the requested vertex count, we move that task to the task buffer here. Each computing thread keeps calling pop to take tasks for processing, and calling push to compute the ready tasks and add them to the task queue if more processing needed. Newly created tasks are also appended to the task queue, and tasks may be spilled to the disk. Remark that if vertex cache or task containers reach their capacity limit, we only repeat the push function to process ready tasks so that vertices can be released from the cache to make room. And pop can then be restored to request more vertices for new tasks. For tasks during between machines, we will estimate the pending tasks in each machine from the capacity of the local vertex table and task files buffered on the disk, for deciding effective task scheduling plans. Tasks stolen from other machines are appended to our file list on disk to be refilled into the task queues of the computing threads. As you can see here, G-Syncer is orders of magnitude faster than other systems, especially for big graphs. The only competitor is gminer, which can scale with the number of CPU cores used, but it does not scale well when the graph gets big, due to its bad task scheduling scheme that keeps a lot of partially computed tasks on disks. Thanks for your attention, and please check out our systems online.
Thank you, everyone. If you have any questions, please feel free to ask.
All right, don't be shy now. Well, it seems like there are no takers for any questions. So I'd like to thank Da again for a very interesting talk.
Thank you.
And I guess at this point, that concludes this session. Thank you all very much for attending. A 30-minute break is following before the next sessions begin. Thank you all.